want to talk about a few questions from chapter 23's book problems. Specifically, we're going to look at number 1 and number 3 and 4 on this page. Number 1, it kind of explores the idea of talking about inverse T and T-CDF in the same light that we used to do normal CDF and inverse norm. The difference here is we're dealing with a t-score, not a z-score, so that's why we're using inverse t. The input for inverse t is the area, the percentile, that's the area to the bottom down here to the left of a value you're looking for, and then degree of freedom. If you have a newer calculator, it's going to ask you for these inputs. If your calculator is a little older, if it hasn't been updated, it may only give you inverse t with parentheses. That's not a big deal. You're going to type in the area, then use the comma button that's right above 7, and to input these two values. The same thing goes for T-CDF. It'll be the lower, the upper, and the degree of freedom, just kind of like it was above, and you're going to use the comma to separate those values. For number 1A, it says if you had a 90% confidence interval, so it looks like this, then what is the critical value for a degree of freedom of 17? Which means I want to know the t-scores that mark off that 90%. Which means that if 90% exists here, then a certain percentage exists down below each one. That would mean that I have 5% down here and 5% up here to accommodate that 100% total. So we're going to be using 5% as my area under the curve. And so we inverse t, 0.05 and 17, and then we're going to be just looking at the critical value. If I do this, I don't get 1.74. I actually get a negative number, which corresponds to the value below the mean. A critical value is always a positive one, right? So it doesn't matter whether I did 5% or 95%. If you add the two areas together, I'm still going to get this particular value, and that's perfectly fine. For B, it's the same scenario, except this time you're using a 98% interval, right? In this case, that means it leaves 1% in each tail, which allows me to just use 0.01 and 88, which gives me 2.37. Letter C, this one's talking about a p-value of t is greater than or equal to 2.09 with 4 degrees of freedom. So I want to know a p-value. That's a probability. That's a normal CDF kind of idea, right? So we're going to be using T-CDF here. Be careful. The equal to part here and the symbol greater than here, these two things do not have any difference in meaning for what we do. Whether it's equal to or not, I'm still going to use 2.09 or 1.78 as my actual interval endpoint. So don't try to think, oh, well, I need to use 1.77. No. Use the exact number, don't change it. Here we're going to be going greater than 2.09. So if I were to draw the curve out like this, we're going to be labeling that critical number 2.09. That's the t-score, and I want an area above that value when we have 4 degrees of freedom. So set that up just like this. We have T-CDF, 2.09, 1E99, and then 0.04. Do that, and it tells you it's 0.0542. With D, we throw in this absolute value. What that really means is you have any value, any t-score, any absolute value greater than 1.78. Well, that would mean 1.79. That would mean even negative 1.79. Right? So that means I'm going to be going out both tails beyond 1.78 or the negative 1.78. So we can do this in a number of ways. Number one, the easiest way is to realize that this whole graph is symmetric and I'm exactly the same distance on either side of my center, which means that I can simply find the area of 1 and double it. That would give me the exact same area of finding this, then finding that, and adding them together. The other way we could do this is we could use the endpoints here and find the middle part here and then subtract that result from 1. That'll give you the exact same answer both times. I just went 2 times the T-CDF, the negative 1E99 up to negative 1.78 with the 22 degrees of freedom. That gives me 0.0444, and I double that value to get 0.0889. I just rounded it to 4 places. Always go to 4 places with p-values. And number 2, I'm not going to talk about number 2 because it's exactly the same process. You can kind of do that for yourself, but it's good practice. Number 3, it says describe how shape, center, and spread of T models change as the number of degrees of freedom increases. This question here. There's no numbers here, and so you're like, well, how am I supposed to describe it? It's just a general description. First of all, T-scores, T models, just like the normal models, are all unimodal and symmetric. So the shape as degree of freedom increases will not change. But you're thinking, well, doesn't it become more normal? Yes, but normality is not technically a shape. The shape of a normal distribution is bell-shaped and unimodal. So as that increases, the sample size or the degree of freedom increases, I'm not changing the shape at all. The center will also remain exactly what the true center is. The spread will shrink as the standard deviation gets larger, or as the sample size gets larger, which in fact makes my degree of freedom get larger. So we have the shape staying the same, the center staying the same, and the spread shrinking so that these t-curves eventually approach what we would consider the normal model or the z-score curve. Number 4, kind of expressing the same ideas here, describe how the critical value of t equal to for a 95% interval changes as degree of freedom increases. They're using 95% here for a particular reason. The z-score critical value for 95% is 1.96. And as my degree of freedom increases, that spread is shrinking, meaning the values out here eventually get closer and closer and closer to a certain value. They don't get closer to 0 and then stop. They're going to stop at their z-scores. So the t-score is trying to estimate a z-score. And so as my sample size increases, the t-scores will get closer and closer to their z-score counterparts. And you get there about right around 4 or 500, sample size of 4 or 500, you will see the t-scores pretty much kind of get right on that z-score and stop. You can observe this very clearly if you'll get your formula sheet out, look at the t-chart, start up at 1 on the degree of freedom of 1, and just walk down that list and use the 95% column. What you'll notice is you have a very large t-score to start with, and it gets smaller and smaller and smaller, and eventually it gets very, very close to 1.96. Eventually it becomes 1.96. You don't have as much detail there, but you could always play around with it in a calculator, but you can trust me on that too. Here we have an example of the conclusion for a confidence interval. The question you had to figure out was which one's the right one. I've written down just some reasons why they're false or it's correct. Don't let this kind of question pass you by. Although this may be a simple question, can you identify why each one is wrong? That really does help you to identify the correct ones even when it's a little confusing. Letter A, it says 95% of all students. Okay, that's already wrong. It's not 95% of all students. It's you're 95% confident, or 95% of the samples taken. In this case, they're also telling you that it's going to be exactly 1102 to 1209 or 1290. There's not going to be any student, or 95% of all students are going to be between exactly this number and exactly this number. That's incorrect. 95% of the sample students paid. I know exactly what happened in the sample. I made the sample. I took the sample. I don't need to be 95% sure or any of that. Okay. Here again, it's also really not discussing the average result either. In C, we're 95% sure. It starts off pretty good. The students in this sample, no, you are 100% sure about everything in that sample. So big problem here. If you got a confidence interval conclusion talking about the sample results, it's wrong. And then D, a lot of us today wanted to go with D or E as the correct answer. In 95% of all samples, it starts off kind of like describing that how we used to describe the 95%. 95% of all samples of students will have an average food, and there again, it goes into the 95%. It's not 90% of all samples of students. It's 95% of samples will produce a confidence interval. So they're really kind of mixing up some results here, and this is a big problem. And then the bottom does a pretty good job. We're 95% sure that the average amount of students will pay between $1,102 and $1,290. So E obviously sounds the most correct and clearly is, because it describes the population and it's using average results to describe it. And finally, number 11. Here we have a graph of compensations in millions of dollars for CEOs. The question was, they did an interval and they got a 95% interval. Let's talk about the mean annual income compensation was between 1.69 million and $14.2 million. Why should you be hesitant to trust this interval? There's a number of reasons here. We have a sample size of 20. So a little bit of skewedness is okay with the nearly normal condition. And you might describe this as slightly skewed. But what we realize here is that we have an average of 7.946 million, which means my average is right in here, between $0 and $10 million. But that average includes this outlier, which means that the average is extremely high because of this value. So the average probably is way down here, closer to, I don't know, 2, maybe even less million. So I've got a very skewed graph, and that's not even the most important aspect here. This right here says big fat no. There should not have ever have been a confidence interval made. Outliers like this are deal breakers. No way ever should you attempt to do something like this in a confidence interval. So big outlier, big problem, shouldn't be done.